So hello everyone, my name is Thomas Galanti. I will talk about SGD Noise and low-rank bias in deep neural networks. Very happy to be here. This is a collaboration with Zachary Sigo, Aparna Gupta, and Tommaso Poggio. So before I jump into our work and all of that, I just want to give a short overview of things that we're probably all familiar with. So in classical machine learning, we typically have this idea of that generalization behaves like a bias-variance trade-off, where we have two extremes. On one side, we have underfitting. The model is unable to fit most of the training samples. And in the other side, we have overfitting, where the model is very large and is able to perfectly fit each one of the training samples, but does not generalize to new samples. And there is this idea that we want to explore this sweet spot between the two regimes, where the model is kind of balanced and is able to fit the data and to generalize to new samples as well. And typically, in order to control this trade-off, we use regularization. And the idea is, as we all know, is to limit the capacity of the model, typically by adding some constraint to regularize or force that the model would be low complexity. But in practice, we see that we can train big models that are larger than the data set, and generalization still occurs, even without or with very little amount of explicit regularization. And one of the hypotheses or the research directions in order to solve and to understand this phenomenon is the idea of implicit regularization. Essentially, that the idea is that the optimizer in a certain way induces a bias of low complexity when training neural networks. So essentially, without explicit regularization, the optimizer, let's say SGD, is selecting or favoring solutions that have low complexity. And certain papers suggested different notions of complexity and tried to show that in different regimes, these quantities are being minimized by like standard optimizers that we care about. So for example, for linear models, it is quite well known that gradient descent kind of implicitly minimizes the norm when we optimize least squares problems. And other papers showed that gradient descent converges to minimum nuclear norm solutions for for matrix factorization problems. And other papers looked at the regime of linearly separable data and showed that we learn rank 1 matrices in that case for certain loss functions. So basically the idea is that different papers try to come up with different regimes and different complexity measures and try to show that in these regimes these measures are being minimized. And overall, what we would like to understand is why SGD is able to generalize well, even when we train without weight decay. And beyond that, maybe to understand how different hyperparameters are able to affect this implicit regularization, whether the batch size or the learning rate have crucial effects on the minimization of these quantities. So in this work, basically we focus on two inductive biases. The first one is the low-rank bias, so whether the optimizer is implicitly minimizing the rank of the weight matrices that we learn. And the second thing is the inherent noise in SGD, whether it is able or unable to converge even if we train for infinitely many iterations. Okay, so we consider a very broad setting. We have SGD together with or without weight decay, and we also incorporate something we call weight normalization. The network may have many different kind of modules like residual connections and so on. But in this talk, I will just focus on standard multi-layer perceptrons. So we have like a product of weight matrices interlaced with ReLU activations. And we start by decomposing the network into two parts. We have the norm of the network, which is the product of the Frobenius norms of the weight matrices. And we have the normalized network, which is the same neural network, but the weight matrices are now normalized. Okay, so the first quantity, we call it rho, and the second one is GV. So V are the normalized matrices. Okay, so we would like to minimize the following objective. Okay, so we have a standard loss. This is like an average over losses. We have weight decay. Okay, so we have a regularization term over the norm rho. And we also have a constraint to enforce that the weights are normalized. So VK are normalized. Okay, so we have this disentanglement between the two, and to ensure that the weights are normalized, we have Lagrange multipliers to enforce that. And basically, in this regime, we optimize VKs and rho kind of independently. So they are trained together, but each one has its own step. And without going into too much detail, these are the gradients of each one of the terms that we consider here. And if we apply it for SGD, so we basically sample a batch in each iteration, and we can look at the steps for the specific batch that we consider. And it is obvious that if we take lambda, if we take the regularization to be 0, then we can just perfectly fit the data if, let's say, we consider MSE loss. But otherwise, the derivatives of the loss function with respect to the output could be 0. And in that case, basically, the gradients are going to be 0 across all batches. Okay, so we get convergence for free when we perfectly fit the data in the unregularized case. So we call this property strict convergence when the gradients are uniformly 0 across all batches. This is slightly different than the original idea of convergence where we have, when we consider a critical point. But just to understand whether we have we have noise, whether we always make steps, we talk about this idea of strict convergence. And this is a very simple lemma showing that if we apply weight decay, if we have non-zero regularization, any strict convergence point is going to be equivalent to 0. Okay, or the data lies on a one-dimensional space, which is unrealistic. Okay, so unless we just converge to 0, there is no convergence. So in practical settings, we just don't have convergence. So SGD strict convergence is impossible when incorporating regularization. But there is another question: what happens near convergence? Okay, whether we are able to see some structure emerging that is not just like being 0 near convergence. So we consider the following setting. We assume that the average of the norm of a step is going to be small when averaging across batches. Okay, so the expected next step is assumed to be small. So we want to understand what kind of structure can we get from that. So the step looks like that. and we assume that the left-hand side is small. So on the right-hand side, we have Vk times some quantity minus some sum of matrices. Okay? And because we assume that the network is one-dimensional, then basically what we get is Vk times some scalar minus some sum of weighted sum of the gradients of G with respect to Vk. Okay, so we have Vk times some scalar minus some sum of gradients, basically. And then we show the following result, claiming that the gradient of the rank of the gradient of G with respect to any one of its weight matrices is at most 1. Okay, so these gradients are just rank 1 matrices. And going back to the gradient, we see that on one side we have V times a scalar. On the other side, we have a sum of rank 1 matrices. So we get a rank B matrix. So we have two terms here. We have something that is proportional to Vk. And on the other side, we have something that is rank at most B, which is the batch size. And we assumed that on average, these gradients are small. So in a sense, we get a trade-off here. Okay? So we have Vk is kind of proportional to a rank B matrix, assuming that these gradients are small. We also see, we could imagine that if we take B to be smaller, then we expect the rank to be smaller in that case, but at the same time, maybe it's harder to minimize the gradients. And also weight decay has some effect here, because if we increase the weight decay, then we expect the derivatives of the losses to be larger. So the coefficient of Vk, the scalar here, is growing with the weight decay, and so on. But essentially, what we see is that we have this trade-off emerging between the batch size, the optimizer, and the weight decay. So as a next step, we wanted to see experimentally if these intuitions actually materialize in practice. So in our experiments, we train models on CIFAR-10 for 500 epochs, and basically we fix all of the hyperparameters except for, let's say, the batch size or any other hyperparameter, and we try to understand how varying this hyperparameter is going to change, to affect the rank of the learned matrices. Okay, so basically we report the average rank across the weight matrices along the network, and the rank is just computed as the number of singular values that exceed a certain threshold after normalizing the weight matrices. Okay, so we look at these VKs. So in these plots, for example, we see that like x-axis is the number of the epoch, and the y-axis is the average rank, and we train the model, the same model with the same hyperparameter while varying the batch size, and we can see that when decreasing the batch size, then the rank decreases accordingly. So for smaller batch sizes, we expect to have smaller ranks. So we did it for 2 cases here, corresponding to 2 different learning grades. Okay, so this is like a very simple 10-layered MLP of width 100 trained on CIFAR-10. And we also considered what happens when varying the weight decay. So we trained ResNet 18, and we vary the weight decay in this case. And we have 2 plots here for batch size 4 and batch size 16. And we can see that when considering larger weight decay parameter, then we get smaller and smaller average rank. Okay? And interestingly, we can see that if we don't incorporate weight decay, it seems that we have little or no rank minimization. So the effect on rank does not seem to occur when we don't use weight decay. So it's kind of necessary in a way. And we also see here that using the smaller batch size gives us, again, the smaller rank. Okay, so some more evidence for that. Yeah, and then we try to understand whether there is a connection somehow with generalization. So essentially, we can kind of see that there is a tendency where if I alter a certain hyperparameter, let's say I take the batch size to be smaller or I increase the weight decay, then I get smaller rank. But obviously, if I take these constraints to be too strong, then eventually the train would deteriorate. I would get very bad train accuracies. But if I consider cases where I vary a certain hyperparameter, but I can ensure that I have a fair comparison, so all of my models have 100% accuracy on the train, then if I compare their test performance, I can see that the one with the lowest rank is the best performing one at test time. Okay, so that in this case, it's the one that corresponds to having the smallest batch size. Okay, and so basically the dashed lines are the test performance, and the undashed ones, the continuous curves, are the train performance. Okay, but at the same time, we see that even when we don't have this rank minimization constraint, the networks are able to perform quite reasonable. It's not like it's necessary to have this constraint in order to obtain a certain reasonable degree of test performance. So to summarize, basically we see that kind of hyperparameters regularize the rank. Empirically and in a way also theoretically, we see that the weight decay or regularization, even very little regularization, is necessary to obtain this rank minimization constraint that we see. And we also see that the batch size, weight decay, and the learning rate have some regularizing effect when they're working together with weight decay. And there is this question that comes up whether we're able to use this idea to translate it to a rank minimization or rank regularization technique, which is, in general, I would say, a hard task to do because rank in itself is a discrete quantity of matrices. So it's non-trivial how to do it. And moreover, we show that generalization occurs even, we know that generalization occurs even when we don't use weight decay. So, it seems that rank minimization is kind of related to using weight decay. So we kind of refute or at least show some evidence against this hypothesis that maybe rank is the explanation why neural networks are able to generalize well in practice in spite of overparameterization. Yeah, and now I'm happy to take questions.